Okay, get ready to dive in. You sent us this chapter all about atomic structure and bonding, and wow, it's got some really amazing things in it. Like we're talking about gecko feet and diamonds, and even how scientists are using this knowledge to completely change the future of surgery.
Yeah, it really is incredible, how all of these concepts that we often think of as like abstract actually show up in the real world with like real world applications.
Totally. And speaking of real world, like applications, can we start by talking about those geckos? They can basically like walk on walls and ceilings. What's up with that?
Right, right. Well, the secret is in the millions of microscopic hairs that they have on their toes. It's not just about being sticky, it's something called van der Waals forces.
Van der Waals forces, okay.
So each of these little tiny hairs creates a weak attraction with whatever surface it touches. Now, on their own, these forces are super tiny, but when you've got millions of them working together, all those tiny forces add up. They can hold up the gecko's entire weight.
That's wild. So like even a single toe can support them.
Yeah, even a single toe. It's pretty mind-blowing how something so small can be so powerful. And, scientists are now actually copying this, like, with bio-inspired adhesive tape.
Oh, wow, real?
Yeah, and this tape could be a game changer, especially in medicine. Like, imagine surgeries without stitches or staples. It'd be so much less invasive and could help people heal faster. And that's just one example of how understanding atomic bonding can lead to, like, incredible breakthroughs.
That's amazing. So we've got these geckos showing us just how powerful these tiny atomic forces can be. But before we get into the details of bonding, can we take a step back and talk about the basics of, well, matter, like atoms? You hear about protons, neutrons, electrons. What
Yeah.
are all of these things?
Sure. So every atom has a nucleus, and that's where you find the protons and neutrons. Protons have a positive charge, and neutrons, well, they're neutral, no charge. Then you've got the electrons, and they're zipping around the nucleus, each with a negative charge.
Okay, so the nucleus is like the center, and the electrons are like buzzing
Right.
around it.
That's a great way to picture it. Now, the number of protons in an atom is really important. It's called the atomic number, and it tells you what element the atom is. Like hydrogen has 1 proton, helium has 2, and so on.
So that's how they're organized on the periodic table. Makes sense. But what about atomic mass? Is that just how much the whole atom weighs?
It's a little more complicated than that. Atomic mass mostly comes from the protons and neutrons together. But here's the thing. The number of neutrons can actually change for an element, and that gives you what are called isotopes.
Oh, right, like carbon-12 and carbon-14, they're both carbon, but they have a different number of neutrons.
Exactly.
Yeah.
And the atomic weight you see on the periodic table, it's kind of an average of all the naturally occurring isotopes of that element. That's why you usually see decimals in those numbers.
So we've got this nucleus with its protons and neutrons, and then we've got these electrons kind of like forming a cloud around it. But how are those electrons arranged? Do they just float around randomly?
Not quite. Electron behavior is definitely way more complex than that. And to really get into it, we need to talk about quantum mechanics and atomic models.
Quantum mechanics. That sounds a little intimidating.
It can be, but it's super interesting too. One of the main things to understand is that electron energy is quantized. This means that electrons can only exist at certain energy levels, not just anywhere in between. Imagine it like a staircase. You can only step on the steps, not in the spaces between them.
Okay, I see. So electrons have these specific energy levels.
Mm.
But how do we know which level an electron is in?
Well, that's where these things called quantum numbers come in. Each electron in an atom has a unique set of 4 quantum numbers. Each of those numbers tells you something about the electron's behavior and energy. It's almost like an address for each electron within the atom.
So it's like each electron has its own like ID card
Yeah,
based on its energy and where it is.
that's a great way to think about it. And these quantum numbers are really important because they help us understand how all those electrons are organized in an atom. And eventually, that tells us how atoms are going to interact with each other to form bonds.
It sounds like these ideas that might seem really abstract are actually super important for understanding how literally everything around us is put
Well,
together.
absolutely. From what materials are made of to the reactions that make life possible, it all comes back to these basic principles of atomic structure and how electrons behave.
Wow, that's amazing. So we know that electrons are super important in the world of atoms, but how do their specific arrangements lead to all these different elements and all their unique properties? Is there any kind of pattern to it all?
There is, and to see that pattern, we have to look at the periodic table. It's not just a random chart of elements, it's carefully organized based on how the electrons are arranged.
Ah, the periodic table.
Mhm.
I feel like every chemistry student has a love-hate relationship with it. but it definitely has a lot of information packed into it.
It really does. And the elements that are in the same column or group, they all share similar electron arrangements in their outermost shell, and that gives them similar chemical and physical properties. Like on the far right, you have the noble gases, and they're known for being stable and not very reactive. That's because they have a full outer shell of electrons, so they're happy just as they are.
So they're like the introverts of the periodic table, perfectly content being by themselves.
Exactly. But most other elements, they're more like social butterflies. They want to interact and form bonds so they can get that stable electron configuration. And that brings us to bonding.
Okay, so bonding is basically atoms trying to get that stable electron configuration. But how do they actually do it? What are the different kinds of bonds?
So there are three main types: ionic, covalent, and metallic. They each have different ways of reaching that stable electron configuration.
Okay, let's break those down. What about ionic bonds? I think those are where electrons get transferred from one atom to
Yeah.
another, right?
Yeah, that's a good way to think about it. Think of something like table salt, which is sodium chloride. Sodium is a metal, and it's happy to give up its outermost electron. Chlorine is a nonmetal, and it's happy to take it. So what happens is you end up with a positively charged sodium ion and a negatively charged chloride ion.
And then, because opposites attract, those charges pull them together, and that creates the ionic bond, right?
You got it. And this kind of bond is common in things like ceramics. It gives them properties like hardness and brittleness. They also tend to be good insulators.
Okay, so ionic bonds are about giving and taking electrons. What about covalent bonds? Aren't those more about sharing?
You're right. In covalent bonds, atoms share electrons to get to that stable configuration. Like in a diamond, each carbon atom shares electrons with four of its neighbors, and that creates a super strong network.
Ah, so that's why diamonds are so strong and valuable.
Exactly. And covalent bonds are also super common in polymers. Those are those long chains of carbon atoms that can be arranged in all sorts of ways to create different materials.
So ionic bonds are about transferring electrons, covalent bonds are about sharing them, and then what about metallic bonds? What's going on with those?
Well, metallic bonds are kind of unique. In metals, the valence electrons, the ones in the outermost shell, they don't belong to any specific atom. They just kind of roam around freely.
Oh, wow. So it's like they're all sharing and moving around.
Exactly. It's like a sea of electrons surrounding all those positively charged metal ions.
That's cool. And is that what gives metals their properties, like being good conductors of electricity?
Yeah, exactly. That free flow of electrons is what makes metals so good at conducting electricity, and it also explains why they're shiny and why they can be bent and shaped easily.
This is making so much more sense now, from how geckos can stick to things to why diamonds are so hard and how electricity flows through wires. It all comes back to how those atoms and their electrons are interacting.
Exactly. These basic ideas about atomic structure and bonding, they're the key to understanding the world around us. And we've only just scratched the surface. There's so much more to learn.
Well, I'm already hooked. So what other cool things are we going to find out about atomic structure and bonding?
Well, for one thing, there's more to bonding than just those three main types. We also have what are called secondary bonds, and even though they're weaker, they still play a big role in how molecules behave and what properties materials have.
Okay, so weaker bonds, but still important. This is getting more and more interesting. I can't wait to hear more about these secondary bonds and what other secrets the world of atoms has to offer.
It's really fascinating how these secondary bonds, even though they're weaker, can really influence how molecules behave. It's like they're not the main stars, but they're definitely important supporting actors.
Yeah, totally. So can you tell me a bit more about them? Like, what are some examples of these secondary bonds?
Sure, so let's start with hydrogen bonds. These are kind of a special case of what we call dipole interactions.
Dipole interactions. Okay. Remind me what those are again.
So basically, dipole interactions happen when you have polar molecules. Those are molecules where one end is a little bit more positive and the other end is a little bit more negative, like a magnet, sort of.
Got it.
Now, with hydrogen bonds, they form when a hydrogen atom is bonded to a really electronegative atom, like oxygen, fluorine, or nitrogen. You see, because hydrogen only has one electron, when it shares that electron in a covalent bond with one of these, electron-hungry atoms, its nucleus kind of gets a little exposed. And the nucleus of a hydrogen atom is just a single proton.
So it's like the hydrogen is left with its positive charge kind of sticking out.
That's a great way to put it. And that exposed proton, because it has a positive charge, it's really attracted to the negative end of other nearby molecules. And that attraction, that's the hydrogen bond.
Oh, I see. So it's like a tiny tug of war between molecules.
Exactly. And even though each hydrogen bond is pretty weak on its own, when you have a lot of them together, they can add up to a pretty strong force.
This is making me think about water. It has a much higher boiling point than you'd expect for a molecule that's so small. Is that because of hydrogen bonds?
You got it. Water molecules are very polar, with the oxygen atom having a slightly negative charge and the hydrogen atoms having slightly positive charges. And that leads to a whole lot of hydrogen bonding between water molecules, making them stick together more tightly.
Ah, so that's why it takes so much energy to boil water. You have to break all those hydrogen bonds first.
Precisely. And it's not just the boiling point. Hydrogen bonds also explain why water can dissolve so many things, why it has high surface tension, and even why ice floats.
Wait, what? How do hydrogen bonds make ice float?
So when water freezes, those hydrogen bonds lock the water molecules into a very specific crystal structure. And that structure is actually less dense than liquid water. So ice, because it's less dense, it floats on top of the liquid water.
Wow, that's amazing. So these hydrogen bonds that seem so tiny, they're actually having a huge impact on the properties of water and, all of life on Earth.
They really are. Now, besides hydrogen bonds, we also have van der Waals forces. These are generally weaker than hydrogen bonds, and they happen because of tiny fluctuations in how electrons are distributed within molecules.
So even molecules that aren't polar, like the ones we were talking about with dipole interactions, they can still have these forces.
Yes, exactly. Even nonpolar molecules can have these temporary shifts in their electron distribution. And those shifts can create little temporary dipoles, like really tiny magnets. And those temporary dipoles can then induce other dipoles in nearby molecules, leading to these weak attractions.
So like even these neutral molecules can get a little bit sticky sometimes.
That's a good way to think about it. And even though these van der Waals forces are very weak individually, when you have lots and lots of molecules interacting, they can become significant.
So it's kind of like the cumulative effect we saw with hydrogen bonds, right? Yeah. A bunch of tiny forces adding up to something bigger.
Exactly. And these van der Waals forces, they're responsible for a lot of things, like how gases condense into liquids, how some things stick together, and even how molecules interact in biological systems.
So van der Waals forces are weaker than hydrogen bonds, but they're still playing a big role in lots of different ways.
Yeah.
And doesn't this take us back to those geckos we were talking about earlier?
You got it. Remember those millions of tiny hairs on their feet? They're actually taking advantage of van der Waals forces to create that amazing grip.
Wow, it's incredible how nature has figured out how to use these tiny forces to do such cool things.
It really is. And it just shows how interconnected everything is, how even the smallest details can have a big impact on the world around us.
So we've covered these secondary bonds, hydrogen bonds, and van der Waals forces, and we've seen that they're both weaker than those primary types, but still really important in all sorts of ways. Where do we go from here?
Well, now that we've got a good understanding of these different kinds of bonds and how they affect how molecules behave, I think it's time to dive a bit deeper into the world of electrons and how they're arranged within atoms. Remember those quantum numbers we talked about before?
Oh yeah, the electron ID cards.
Yeah.
So those are more than just numbers. They actually affect how molecules behave.
Exactly. And they're especially important when we start talking about hybrid orbitals.
Hybrid orbitals, what are those?
Well, we know that electrons occupy these specific orbitals within atoms, right? Like the SPD and F orbitals, they all have their own unique shapes and energy levels. But sometimes these atomic orbitals can actually combine to form what we call hybrid orbitals.
Combine. So it's like they're mixing and matching to create something new.
That's a great analogy. And these hybrid orbitals, they have different shapes and energy levels than the original atomic orbitals. They're really important for determining the shape of molecules and the angles between bonds.
So it's not just random. The way the atoms are arranged in a molecule, that's determined by these hybrid orbitals.
Exactly. For example, let's look at carbon. Carbon has 4 valence electrons, and it often forms 4 equivalent sp3 hybrid orbitals. And that gives rise to this tetrahedral shape that we see in molecules like methane, where the carbon atom is in the center and the 4 hydrogen atoms are at the corners of a tetrahedron.
So the way those 4 bonds are arranged, that's not just by chance. It's because of those p3 hybrid orbitals. And that tetrahedral shape, that affects how that molecule interacts with other molecules, right?
Absolutely. It influences its properties and how it fits into bigger structures. Understanding hybrid orbitals is essential for understanding how molecules work in 3 dimensions.
Okay, hybrid orbitals are shaping the molecular world, but how does this all connect back to materials and their properties? It feels like there's a bigger picture here.
You're right, all of these concepts about bonding, the types of bonds, the influence of hybrid orbitals, they all come together to determine the properties of materials, like how strong a material is, its melting point, its ability to conduct electricity, how flexible it is. All of that is affected by the types of bonds between atoms and how those atoms are arranged in space.
Wow, it's like a chain reaction. Starting with those tiny atomic orbitals, we see how they create bonds, shape molecules, and ultimately determine what the materials we use every day are like.
It really is remarkable. It's this flow from the microscopic world to the macroscopic world, all governed by these fundamental principles of atomic structure and bonding.
It's incredible to think about,
Yeah.
and to think we've only just begun to explore this.
Yeah, it's really amazing how it all goes back to these basic ideas about atomic structure and bonding. We've talked about gecko feet, we've talked about diamonds, water, hybrid orbitals. It's crazy how all these things that seem so different are actually connected by these tiny particles and the forces between them. It really does show you just how beautiful and interconnected the natural world is, and being able to see those connections, how the microscopic world influences the macroscopic world. That's what opens up all sorts of possibilities, especially in material science.
Material science, so that's like all about designing and making new materials with specific properties, right?
Exactly. And understanding atomic structure and bonding is like the foundation for all of that. By knowing how atoms interact, how they form bonds, how the way they're arranged affects the material's properties, we can basically create materials that are exactly what we need.
So instead of just, finding a material that happens to have the properties we want, we can actually design them from scratch.
Exactly. Think about things like, the super strong alloys they use in airplanes, or those advanced ceramics that can handle crazy high temperatures in jet engines. We couldn't have those without understanding atomic bonding and how it all works. It's incredible. So by changing the types of bonds, how the atoms are arranged, we can create materials that are stronger, lighter, more resistant to heat, all sorts of things. Like we have this toolkit for building materials.
That's a great way to put it. And we're always adding new tools to that toolkit as we learn more and more about these basic principles.
Mm.
Take polymers, for example. Those long chains of molecules held together by covalent bonds, they can have so many different properties depending on how they're structured and how they interact.
Right, polymers. I mean, think about plastics, the fabrics in our clothes, they're everywhere.
Exactly. And by changing the types of monomers, the little building blocks of polymers, and how they're connected, we can create materials that are flexible or rigid, transparent or opaque, you name it.
It's mind-blowing to think that we can control these properties at such a tiny level just by understanding how atoms work. It's like we've unlocked some kind of secret code for the material world. And that code is always evolving as we keep learning more about atomic structure and bonding. We've covered a lot in this deep dive, but there's still so much more to discover.
I know, it feels like we've just scratched the surface. There's all this stuff about quantum mechanics, different crystal structures, semiconductors. It's a little overwhelming, but in a good way.
It really shows you the power of scientific curiosity. From seeing a gecko sticking to a wall to creating new materials that can save lives, it all comes from that drive to understand the world around us at the most basic level.
And that understanding gives us so much potential for innovation and solving problems. It's really inspiring to see how something as seemingly abstract as atomic structure can actually have such a real impact on our lives.
I completely agree. It reminds us that there are so many amazing things in the world waiting to be discovered.
Well, you've definitely gotten me excited about all of this. I'm ready to learn even more about this fascinating world of atoms and bonds. Thanks for being such a great guide on this deep dive. I really enjoyed it.
The pleasure was all mine. Keep exploring, keep asking questions, and you never know what you might find.